So in this chapter, we're going to be talking about titrations between acids and bases, and the pH, which you're probably familiar with just generally. If you ever measured the pH of your pool, things like that. We're going to learn what pH stands for, or what it tells us. So we're going to talk about ionization of water, how it ionizes into those two ions we've been talking about, the hydronium and the hydroxide. We're going to define pH and use the pH scale. We're going to also do some calculations where, given the concentration of hydronium, we're going to be able to find pH or the concentration of hydroxide. So, what is the self-ionization of water? Basically, it's two water molecules that produce a hydronium ion and a hydroxide ion by transferring a proton from one to the other. So, if we take a H plus from this hydrogen, or from this water, and you give it to this water over here, you're going to see this will gain an H and a plus, becomes H3O plus. This will lose an H, so it's only OH, and it's a minus. You guys all see how the transfer happens. The H plus is given from one water, and it's taken to another. I might have said it backwards. The one that gives the H plus is this one. The one that accepts the H plus is this one. So in water, at 25 degrees, pure water, that is, we're going to see a concentration of 1.0 times 10 to the negative 7th molar. Remember, molar means moles per liter. So if I have a liter of water, I'm expecting to see 1.0 times 10 to the negative 7th water molecules, moles of water molecules become hydronium, and then 1.07 times 10 to the negative 7th moles per liter will become hydroxide. So we have a constant called Kw that if we multiply those two numbers together, it's always going to give us the same number. So for water specifically, if I take 1.0 times 10 to the negative 7th times 1.0 times 10 to the negative 7th, that gives me Kw. Does anybody know what 1.0 times 10 to the negative 7th times 1.0 times 10 to the negative 7th would be? What do I do with exponents when I multiply them? You add them. So negative 7 plus negative 7 is negative 14. So for water, that's exactly right. This is going to be 1.0 times 10 to the negative 14. It should be somewhere here. Right there. So 1.0 times 10 to the negative 14. Notice it changes at different temperatures because it'll ionize differently. It ionizes more at higher temperatures. So we see that value go up if I heat up the water. But in general, Kw is going to be 1.0 times 10 to the negative 14. 14 and the 7 are kind of important, as we'll see. But we need to define acidic and basic solutions. We sort of talked about them qualitatively last chapter. We said, acids taste sour. Bases, they taste bitter. They're slippery. This time we're going to define it mathematically. Solutions where the hydronium count equals the hydroxide concentration are neutral. And I should point out these brackets mean concentration. So my molarities basically. So where the molarity of hydronium equals molarity of hydroxide, that's neutral. That's pure distilled water. Where the hydronium count overtakes the hydroxide count, that's acidic. So that would mean that hydronium is concentration greater than 1.0 times 10 to the negative 7th. On the other hand, basic solutions would mean my concentration of hydroxides is greater than 1 times 10 to the negative 7th molar. So this is from last chapter 2, but strong acids are acids that are completely dissolved. Weak acids do not completely dissolve. So a strong acid might look like, or I guess this is a base, NaOH here, where it breaks down completely into sodium ions and hydroxide ions. So because we're getting a lot of those hydroxide ions, we're looking at a base because that's going to increase the concentration of hydroxide from 1 times 10 to the negative 7th. It's going to increase it to 1 times 10 to the negative 2nd if that's the concentration. And we can calculate the hydronium concentration by understanding that my Kw equals hydronium concentration times hydroxide. And it always equals 1.0 times 10 to the negative 14th. So if I know I have a concentration of OH as 1 times 10 to the negative 2nd, I can figure out the hydronium concentration by taking this number divided by my hydroxide concentration. So hydronium is Kw over hydroxide. So that's 1 times 10 to the negative 14th over 1 times 10 to the negative 2nd. And to subtract them, you're going to get 1 times 10 to the negative 2nd. So what this is telling me is if I know one, I can find the other, and vice versa. I just take 1.0 times 10 to the negative 14th divided by the other one. Should be an example coming up soon here of that. Maybe not. I guess, yeah, sample problem A. This is just showing me the reverse. If I know the hydronium count, I can do the opposite to find hydroxide. So if I know, for instance, that I have the HCl, it's a strong acid that will completely dissociate. So if my acid has a concentration of 2 times 10 to the negative 4th molar, that means my hydronium will have a concentration of 2 times 10 to the negative 4th molar. So hydronium concentration times hydroxide concentration gives me 1 times 10 to the negative 14th. So if I take 1 times 10 to the negative 14th divided by my hydronium, that will give me my hydroxide, which is 5 times 10 to the negative 10th molar. We're going to do an example of that together so you can see it worked out. But this is just a chart for you so you can see some different strengths of acids. See, the stronger ones would be the hydronium ion itself with its conjugate base shown there. Then you can see how the concentration of the hydronium times the concentration of hydroxide will always give me Kw, which is 1 times 10 to the negative 14th. So my example, a 1 times 10 to the negative 4th molar solution of HNO3 has been prepared for a laboratory experiment. If I have 1.0 times 10 to the negative 4th molar of HNO3, my hydronium concentration should just be 1.0 times 10 to the negative 4th molar because that's going to, let's see, HNO3. Guess it's not on my, I thought it would be on my list there. But the key is, because it's a strong acid, it's going to completely dissociate into hydronium ions, and the concentration of the hydronium ion would be the concentration of the acid. And then to calculate the hydroxide ion, we know that the concentration of hydronium times the concentration of hydroxide always has to equal Kw, assuming we're at room temperature. So that's 1 times 10 to the negative 14th. To find OH, I just take 1 times 10 to the negative 14th divided by 1 times 10 to the negative 4th, my hydronium concentration. And then that's just going to be negative 14 minus negative 4. So negative 14 plus 4 should give me 1 times 10 to the negative 10th. Can't read that. It's 1 times 10 to the negative 10th molar. So that little equation makes sense, how the two concentrations multiply and give me the same number each time. Sorry for the confusion there. I just don't know how they expect you to know that if it's not in our list. But so that gives us the pH. That's kind of the main thing we want to look at today is pH. Now, if you're not familiar with logarithms, notice we've been dealing with a really kind of annoyingly small number all this time. We've been looking like times 10 to the negative 4th, times 10 to the negative 14th, times 10 to the negative 7th. It gets really annoying to have to write all those tiny, tiny numbers. So what logarithm will help us do is scale it up so that it's more of like a more reasonable number. Kind of like how they do with GPA. You know, you have your grades, which are all over the place, but then your GPA kind of puts it on a scale. The log will put this on a scale from 0 to 14 so that we have a nice everyday number to describe pH. So pH is going to be the negative log of my hydronium ions concentration. So an example, we know that neutral solution has 1 times 10 to the negative 7 hydronium. So that when I take the negative log of that number, negative log of this number here, I get, the regular log is negative 7, but the reason I make it negative is so we can get rid of that negative 7 and just call it a pH of 7. So the log of 1 times 10 to the negative 7th is just the power of 10. It's negative 7. And then pH, we're saying it's a negative log. So that's where we get saying something has a pH of 7 if it's neutral. So you can see the pattern here. If I have a negative 7 up here, my pH is 7. Negative 1, my pH is 1. As long as the base number is 1, the pH is just the opposite of the power of 10. So 1 times 10 to the negative 12th gives me pH of 12. 1 times negative 10 to the negative 13th gives me pH of 13. There is something we don't use quite as often, but the POH is kind of the opposite. It's just dealing with the hydroxide concentration. So if I had something with a neutral solution would be hydroxide concentration of 1 times 10 to the negative 7th. Therefore, the pH would be 7. The POH is how much I have to add to the pH to get 14. So if the pH is 7 for something, a neutral solution, what do you think the POH would have to be? 7. Yeah, they'd have to add up to 14. So if the pH was 2, POH would be 12. Yeah, you got it. So here's my scale. You can see as I get more acidic, my pH is going down to 0, which people kind of think, or maybe it's just me, but from what I've, just general conversations with people I've had that don't know about pH, they hear a low pH and they think it's not that acidic. Oh, that's pH of 2, it's not that big a deal. But yeah, actually, the closer you get to 0, the more acidic something is. You don't want 0. Same with the other way, like basic. pH of 14 is very basic, so it doesn't mean it's not dangerous. It means it's quite dangerous if it's got a high base, I don't even know how to say that, basicity. But then neutral's right here in 7. So your strong acids down here would be stuff like battery acid, sulfuric acid. Stuff up here with your 14 pH would be like sodium hydroxide that we've got back there making the soap, and drain cleaner, things like of that nature. Oh, and they have conveniently some examples for me here. See, gastric juice, so your stomach acid's got the pH between 1 and 3. Lemons, vinegar, soft drinks, apples, lots of fruits kind of have that slightly acidic. But then milk is a little bit acidic. Notice, where does the stuff we eat usually lie? You see all the stuff up here, up to saliva. It's mostly acidic. Then you got pure water. But then your blood is slightly basic. Eggs are basic. But then, yeah, seawater, milk, and magnesia, things like that. Basic. You notice things you take for heartburn because you have that acid buildup. You're usually going to see on the basic side, like carbon, Tums or calcium carbonate to help reduce that pH level. So again, just a summary of everything. Neutral solutions, your pH is equal to the POH. Acidic solutions, you're going to have a pH less than the POH. So your concentration of hydronium ions is higher. For basic solutions, your concentration of hydroxides is higher. So you have a higher pH than the POH. And these two add together to give you 14. This just talks about sig figs, so really what we're looking at is if I have 1 times 10 to the negative 7th, I have 1 sig fig. So when I'm using logarithms, I have that many sig figs to the right of the decimal. So it's sort of a new thing compared to what we're used to. You can kind of go one further than we normally would in multiplication and division. So let's go ahead and see if we can calculate the pH of 1 times 10 to the negative 3rd sodium hydroxide solution. pH is the negative log of my hydroxide concentration. There's a couple ways we can go about this because we don't know either the pH or the hydronium count. Why is that? I should have asked you, is sodium hydroxide, do you think that's going to be a strong acid or a strong base? I'll give you a hint here. What do you think NaOH is more likely to produce? H3O pluses or OH minuses? Yeah, OH minuses. So that means it's going to be a base. So I can't find the POH, but I could find the I can't find the pH, but I could find the POH. If I take the negative log of that number, you can do it in your calculator. Negative log of 1 times 10 to the negative 13th. So, oh, it's third. Thanks. Good call. Can I erase that? No, I can't. Yeah. Oh, I won't let me erase it. That's annoying. Yeah, you never saw that one there. Go away. So, negative log of 1e negative 3, try that, is 3. And did I really have to use my calculator? Probably not. But I just wanted to show you how you can use a calculator if you have to. But negative log of that is just the power. And it's negative, so it's going to be positive 3. See if you remember. What's that telling me my pH has to be? What do they have? What does pH and pH have to add up to? 14, so my pH is going to be 11. That's not too bad.
It's not too bad
right now, and then yeah, it gets. Let's see. Oh yeah, we can knock this out. Yeah. So, calculations involving pH. This is just a summary of everything. How you would find it. pH is the negative log of the hydronium concentration. So the log of the hydronium concentration is negative pH. That means if I had to find hydronium, if I knew the pH and I had to find the hydronium, I would take the anti-log. Have you ever done the anti-log of negative pH? Basically, the anti-log is just 10 to that power. It's just the reverse. Yeah. Yeah. Yeah, I'm almost done here. So, if I have 10, basically all this is saying is if I knew that the pH was 2, then the hydronium concentration is 10 to the negative 2. Does that make sense? That's all. It sounds complicated, but that's all the anti-log is saying. It's backwards, right? So let's look at it real quick. pH of 4, what's the hydronium concentration? You got it, 10 to the negative 4. Not too bad, right? I keep saying not too bad, and you're waiting for the other shoe to drop here. So here's some pHs of weak acids and weak bases that have to be measured experimentally. I'm going to kind of skip over that. The bell's about to ring. But you can see this is we already talked about some examples. We actually have pH paper. We're going to look at some things. Universal indicators will actually turn the color of what pH something is. So if we put it in apple juice, it'll become yellowish. If we put it in ammonia, it should become bluish. So we'll try, tomorrow I think we'll try some of that out just for fun. And talk about titration. So